All right, we're going to take the conservation of energy to the next level, but before we do, I just have to make sure some definitions are very solid. So write down notes, the conservation of energy, exclamation point. It's important to be enthusiastic. And if you need to pause the video at any time, I'm going to go a little bit quickly just because I want to keep the video short. And if you need to pause it and write down words, that's totally okay. But the qualitative, so using words, definition of the conservation of energy. Conservation of energy. Energy cannot be created or destroyed. It can only be transferred from one form into another. Okay, so qualitative, that just means word description. And so if you ever hear that on the AP test, qualitative goes with words. Quantitative, that's more of a math equation or a number type situation. So some examples I have for conservation of energy. You eat food, then you go to work out. Some people might be like, I'm gonna go work out and destroy that energy. But actually, if you've ever gone to the weight room before, and being a physics teacher, I spent a lot of time there. I will say examples. I ate a pack of Pop-Tarts, and that 400 calories would sit in my belly, and if I didn't do anything about it, it would turn into fat. And I'd use that fat energy maybe later, or maybe I wouldn't use it and it'd just stay there in my belly as fat. But you didn't destroy the energy, it just went from that food type source to stored fat. But maybe you went to work it out and you took that energy, and instead of it getting stored as fat, you burned it off. And you go, and if you've ever walked into the weight room after people have been in there working out for a while, you realize it's pretty warm in there. And so that food energy went to the body, then the body did work, and they gave off heat energy. So it's not that you destroyed it, but it transferred from one form into another. Okay? So chemical potential energy, like through food, to the heat energy in the actual workout space. Another example, and this is kind of what shows up, that doesn't show up on your AP physics test so much. But what does show up on your AP physics test is a sled going down a hill. You have potential energy because you're sitting on top of a hill, so gravity has the potential to do work on the sled system. And then as it goes down the hill, that sled gets going faster and faster, and that's going to transform over to the energy of motion, which is kinetic energy. And at the very bottom of the hill, you have a height of 0 meters, so your PE is all gone, and it's not like it got destroyed, it got transferred over to kinetic energy. Okay, and we're going to talk more about that with some examples, but that's just kind of getting you thinking about it. Now, energy cannot be created or destroyed. That's the qualitative way to say it with words. But if you want to say it with an equation, it's actually a super simple, but a very, 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 and three varies, a very, very, very important equation. Energy initial equals energy final. On the AP physics test, they find opportunities to see if you know this super important principle that energy initial equals energy final. But sometimes they'll write it a little bit differently. They'll subtract the EI over, and they'll say if you take your final energy minus your initial energy, that should be equal to 0 joules. Okay? And keep in mind, in physics class, we use the label joules, capital J, Joules, to label energy. On food labels, they use calories. Technically, they're kilocalories. It's just that they label them like a little bit differently on food labels. It's kind of a tricky thing. When they say 400 calories on a label, like for food, it actually should say 400,000 calories because the food makers actually call it a calorie, but it's actually, they list kilocalories. And we don't need to get into that right now. But that's something I didn't learn until I was in college, that people don't like the metric system so much, so that instead of listing, 400,000 calorie Pop-Tarts, they just say, 400 calories. But technically those are kilocalories in the labels of food. But sometimes you'll actually even see that on protein bars and stuff. They'll call them kcals. But I'll say, don't worry about that. We use joules in physics, and that's our label for energy. So if you take your final energy minus your initial, because those things are the same, that it should be equal to 0 joules. A couple other important things. We use the conservation energy a lot, but energy is a scalar. So you're not going to include an angle. You don't really have a direction. I mean, you can add energy into a system or take it away, but it's not a vector. So you'll never have an angle. You'll just have a number. And you can say, I lost 10 joules or I gained 10 joules, but you're not going to have like an angle component with conservation energy. And so you're not going to have to break energy into how much was in the x direction, how much is in the y direction, because energy is just a scalar, just a number. Okay, so we're going to look at some important definitions, and maybe you already heard about these in the book or maybe from some of the videos, but I want to make sure to highlight these important definitions in this video. Mechanical energy, it's the energy of an object due to its motion and its position. So whenever you're talking about mechanical energy, I always picture like big things like roller coasters or blocks sliding along a ramp or a plane or a car. By plane, I don't mean like an aeroplane, I mean like a incline plane. And I'll say, or a car coming to rest. You're talking about the motion of kinetic kind of stuff. The energy of motion is kinetic energy, or position, which is potential energy. Okay? So you'll hear that phrase, mechanical energy, and I picture big objects like roller coasters and cars and mechanical things. What I don't picture as mechanical energy, that's not like chemical reaction energy. Okay, those are electrons rearranged and things like that. So I will say mechanical energy, the energy of bigger objects moving in space. Okay, some other key definitions. You have forces that are called conservative forces. And a conservative force is when you have transitions between kinetic energy and potential energy, such that when you sum the PE plus KE at any point along the system, it is the same value. And that's a lot of words, and I think if you write it down, that's great, but I'm going to have you write down this picture and it'll make a heck of a lot more sense. Let's picture you're at the top of the roller coaster right here. And if you're at the top of a roller coaster and you're just sitting there stationary, you have no kinetic energy because you're not moving, but you're up in the air a certain height h. So you have all potential energy. Gravity's going to do work on you and bring you down that hill. Okay? So you have all PE, and let's say you have 10 joules. That's a ridiculously small number. I just picked nice, easy numbers. And then as the roller coaster falls, you can picture the height is decreasing, so your potential energy value is getting less, but you're speeding up, so your kinetic energy term is getting greater. So at the top of the roller coaster, you had what? KE was 0 joules. Your PE might have been 10 joules. And if you add 0 plus 10, you have 10 total units of energy right there, 10 joules of energy total. And then halfway here, maybe you have 5 joules of potential, 5 joules of kinetic. So if you sum your potential plus your kinetic, it still totals up to 10. And then at the very bottom, as you're at the very bottom of the roller coaster here, and you have no meters left for your height, so your PE is 0 joules, and now all of your energy is KE, kinetic energy, is 10 joules. So if you take 10 plus 0, your total energy is still 10. So anywhere along the roller coaster ride, if you add up your potential plus kinetic, it's equal to 10. So that's why I say when you have transitions between KE and PE, when they're kind of sloshing back and forth there, when you sum the two numbers, you get the same value throughout. That means that there must be a conservative force acting on it. In this case, it is gravity, which is a conservative force. And your energy is conserved. Important notes, all along the path, the E total is 10 joules. Notice there's no vector sign over the energy because it's a scalar. And conservative forces are path independent. So it doesn't matter how curvy the roller coaster track is. You went from point A at the top to point B here to point C. It only mattered that your height was changing from here to here to here. Now, we all know in real life that if you're on a roller coaster, there is a little friction. So I'm saying we're ignoring friction in this example, and we'll talk about that more in a second. But actually, for the most part, just knowing the height of the Wild Thing roller coaster at Valley Fair, you can, I think last year we calculated within a mile an hour or two how fast it should be going at the bottom of the roller coaster, and we ignored friction and we're pretty darn close. So conservative force, path independent. Now, if you want to talk about something else, it's called a non-conservative force. And I'm sorry my handwriting got a little messy here. It takes energy out of the system or into the system. So if you want to write this down, it takes or adds energy out or into of the system. That's a horrible sentence. Non-conservative force, it can take energy or it can add energy into the system. And so let's do this example. Friction removes energy as heat. And one thing, the conservation of energy isn't violated. It's just that when you, and we'll draw this on the next page, but your system is losing some energy as heat. And when I say lose, that's not really, lose kind of gives the connotation that it's going somewhere you don't know where it is. Well, it went toward heat. We can still sum it up and the energy of our system will be the same. It's just that it's going toward heat. So friction removes energy from our roller coaster system. Or in the second case here, maybe you have a rocket engine and that rocket engine's burning fuel, so it's adding energy into the system. Or maybe you have gasoline in a tank and that's adding energy into the system. And the best way to picture it here, so I said this right here. I said, let's go back to our roller coaster example. And we're at the top of the roller coaster again, and it's just hanging out there. Kinetic energy is 0 joules because it's like you're just hanging on the roller coaster. You're looking down, you're not moving, but you're terrified. And you're like, why did I get on the roller coaster? I have feelings about that a lot, about rides. But I will say, so 10 plus 0, boom, still adds up to 10, right? Then halfway down, let's say your potential energy is 5, but you're not quite going as fast as you thought you would be at the halfway point. Like maybe your kinetic energy value only has 4 joules. And so now 5 plus 4 only equals 9. So your PE plus KE is 9 units instead of the 10 units it should be. Well, that's not because you lost energy, like you don't know where it is. It's just that that energy went toward maybe 1 joule of heat. So this would be an example of a non-conservative force because PE plus KE does not equal what you initially had it to be. And that's just one of those things that we'd have to account for that 1 joule of energy that got transformed to heat. But this would be, let's say there's friction on the track now, you'd have to account for that with your equation. Okay, so we can do that, and we can do that with work, and we'll talk about that in some later examples. But it's just important to note that if there is a non-conservative force, you have to account for that doing work. And in this case, it's negative work because it's removing energy from our system. okay? And then at the very bottom, maybe you're like, okay, I have 8 joules of kinetic, and maybe since I'm at the bottom, I have 0 for my height, so I have 0 joules of potential. And you're like, whoa, I started with 10 total joules, now I'm only accounting for 8. It's because maybe you have 2 joules of friction that causes some heat loss, and so we can account for that in our equation. It's just that that's what they call a non-conservative force, because it's taking energy out of the PE and KE kind of stuff right here. Okay, so that's a great little introduction. We'll stop there. Actually, just to kind of recap here, so non-conservative forces, they depend on the path. So obviously if you had a really long roller coaster track, you're gonna experience more and more friction, so you're gonna have more heat losses. And I can't reiterate this enough. When we say heat losses, we know where the heat's going to, so maybe I should say heat transformations. And so maybe at the end of the thing, you've lost 5 joules to heat energy, and you only have 5 joules of kinetic energy. But no matter what, if you total all your energy up here, it still adds up to 10, because the energy of your system isn't being destroyed. It's just that it's going toward things that you need to account for. So note, if you define your system as the roller coaster cart plus the track and all the surrounding air, right here, the air that might be getting warmed up a little bit here, you're still gonna have about 10 joules of energy in your system. Okay, but the question arises is like, let's call this my system, and maybe you get 9.9 joules and there's 0.1 hanging out really far away now. It's just one of those things in physics, we make approximations, and if I say, oh, all this air right here, it has still about 10 joules around here, 10 joules around here. But that's a great introduction to some key vocab about conservation of energy and conservative and non-conservative forces. But the big takeaway is conservative forces, those are path independent. So that's the first roller coaster example, when it didn't matter how curvy the track was, it just mattered that it dropped a certain height. In the second case, when we account for friction, that's a non-conservative force. Friction is a non-conservative force because it depends on the path. Because the longer you're on the path, the more friction you're going to experience and the more heat losses you're going to generate. Okay, so that's a great place to stop. We're going to do some examples in the next video.